4.5 billion years ago, the newly formed Earth spun with such velocity that a full day lasted between 4 and 6 hours. This chart tracks the steady deceleration of that spin over billions of years. By the time the T-Rex walked the Earth, the day had stretched to 23 hours, eventually arriving at the 24-hour cycle we use to set our clocks today. The planet is losing its rotational energy, and we can measure the exact rate at which our daily clock is being pulled apart. Because the sun's gravity is the dominant force in our solar system, we have to look at how that gravity interacts with time. Albert Einstein proposed that gravity is not a physical pulling force, but a geometric bending of the fabric of space and time. Massive celestial bodies like the sun create physical dents in this fabric. As space curves, time passes slower, a phenomenon called gravitational time dilation. Because Earth orbits deep within the sun's valley, our clocks take slower than a clock in empty space. This creates a direct connection. If the sun's mass physically warps the passage of time, it suggests that this massive gravitational valley is the mechanism stretching our 6-hour primordial day into our modern 24-hour cycle. While the connection is intuitive, it relies on a misunderstanding of how these distinct systems interact. Relativistic time warping is a steady state. The sun's mass created a specific, permanent dent in spacetime billions of years ago. It is not a hole that grows deeper every century. Since the sun's mass hasn't changed significantly, its warp on spacetime remains constant. It cannot be the cause of a day length that is actively and continuously increasing. The elongation of our day belongs to a different domain of physics. We are witnessing the physical slowdown of a spinning object. The primary force at work is the moon's gravitational interaction with Earth's oceans. The moon's gravity creates tidal bulges in the water. As the Earth rotates beneath these bulges, the friction of the moving water against the ocean floors acts as a planetary brake. This friction slowly bleeds away the planet's rotational energy. There was a period called the boring billion, where this slowdown stopped. The sun heats the Earth's atmosphere, creating a thermal tide that pushes the planet to spin faster. For a billion years, this solar push perfectly countered the moon's pull, pausing the day length at 19 hours. Our 24-hour day is the result of a mechanical tug-of-war between the ocean and the atmosphere, functioning independently at the relativistic warping of spacetime. The atmospheric balance eventually broke, allowing the moon to regain its lead. Today, the Earth continues to lose its rotational energy. This mechanical friction adds between 1.7 and 2.3 milliseconds to the length of a day every century. Evidence of this slowdown is recorded in ancient biology. These fossilized growth rings on horn coral confirm that 600 million years ago, the days were so short that a single year contained roughly 420 of them. If this rate of friction remains constant, Earth will reach a 25-hour day in approximately 150 million years. As long as the moon orbits the Earth and the oceans continue to slosh against the seabed, the planet will continue to wind down. We live under two separate rulebooks. The sun's massive gravity dictates the flow of time in our corner of the universe, but the physical friction of our own oceans dictates the speed of the clocks on our walls.